Hello, this is Mohammad Ghoreishi. Welcome to my talk on the agricultural rebound phenomenon, why, what, and how. The important question is what the rebound phenomena is. Modernizing traditional irrigation systems has long been recognized as a means to reduce water losses. However, empirical evidence shows that this practice may not necessarily reduce water use in the long run. In fact, in many cases, the converse is true, a concept known as the rebound phenomenon. This phenomenon can be conceptualized in four phases. In phase one, governments generally introduce conservation policies, for example, technical assistance or financial incentives to adopt more efficient irrigation systems with a specific goal of water saving. In phase two, the agricultural water use almost reaches the predetermined purpose of the program. However, this ideal phase can be followed by the growth phase, an increase in agricultural water use due to several side effects. This pattern may finally lead to phase 4, the backfire phase, in which the new water use is even more than the initial water use. Now we are interested in three different questions in this presentation and research. First, why does such a phenomenon emerge in a river basin? Second, what are the main socio-economic factors controlling the rebound phenomenon over time? Third, how can we avoid the rebound phenomenon in future sustainable water planning? Now let's look at the traditional agriculture water demand model with the effect of water conservation policies. Basically, we assume some scenarios for water conservation policies that can reduce water demand and then increase our water availability. However, this human water system is not as simple as we just saw. In fact, drought as an extreme event affects water availability, leading to a decrease in farmers' crop yields and gross margins. As a result, farmers adapt to a new situation by water conservation through policymakers' subsidy and self-finance, resulting in a decrease in water demand. However, this water conservation, which can increase water availability in a river basin, might encourage farmers to increase their irrigated area. This increase in the irrigated area could increase agricultural water demand, resulting in a reduction in water availability through the other loop. Using systems thinking, these feedback loops can finally result in rebounding water demand in the system. To understand the dynamics of agricultural water demand and the potential rebound phenomenon, we develop a water human model and apply it to Bow River Basin in Alberta, Canada. This slide shows you the timeline of drought in Alberta and the political actions in order to adapt to drought situation. And the last policy in Alberta is Waterfall Life program after 2005. And now the question is, what is the Waterfall Life program in Alberta? The Waterfall Life program was a conservation policy for adaptation to drought. This policy includes two main purposes. First, encouraging farmers to modernizing irrigation systems. You can see a decrease in the area of flood irrigation systems between 2000 and 2015. Also, throughout this policy, the crop patterns in the Bow River Basin were switched from forage to other crops like cereals, oilseeds, and specialty crops which require less water during the growing season. To model this water human system with its feedbacks, we have two main approaches: system dynamics and agent-based modeling. System dynamics as a top-down approach is used when there is a comprehensive knowledge about the entire system and its governing equations. Using this knowledge, researchers attempt to replicate the system structure by modeling system behavior. On the other hand, agent-based modeling, as a bottom-up approach, starts a simulation at the level of an autonomous entity, an agent, which might be a member of a heterogeneous group. By simulating all agents and their possible interaction, researchers attempt to explore possible emergent behaviors and system pathways. In this research, we used agent-based modeling as our approach to model this system. The purpose of our research is to simulate agricultural water demand under the impact of both a water-saving technology and changing crop patterns. We use different data for our model inputs, like crop yields, crop prices, crop production costs, irrigated area, methodological data, conservation target, and subsidy. And our model output are in human submodel. We are providing irrigation system area and crop patterns, and in water submodel we are providing agricultural water demand. Following local studies in our case study and other previous studies, we determined several socio-economic factors relevant to farmers' water conservation decisions. First, the conservation purpose accounts for water conservation targets set by the government. The future profit is based on the expected gross margin of 1 hectare of conservation. In fact, an agent decides to conserve water if he or she earns more benefits by conservation. This benefit can be received by the government subsidy and market. The past profit is based on the same idea, however, the economic evaluation is based on the past information of an agent or the agent's memory. The risk aversion shows the degree to which an agent changes his or her past decision on water conservation. Therefore, if an agent is risk averse, this agent continues his or her last decision on water conservation. The social interaction accounts for the extent to which an agent is affected by neighbors, and the environmental protection factor implies the extent to which an individual farmer conserves water for environmental protection regardless of economic consequences. The irrigation expansion factor shows the amount of water, the saved water that is used for irrigation expansion. Following the literature, we assume each behavioral parameter of farmers as agents is coming from the community normal distribution. Thus, we have 14 parameters in this research, including one mean and one variance for each value. In this research, we assume 2,000 farmers as our agents. We also assume different ways reflecting the degree to which each socioeconomic factor plays a role in a final decision for each individual farmer. Following previous studies, we assume each different way for individual agents is sampled from a normal distribution of the community. In our study, each of the ways was randomly sampled from a normal distribution with the mean and variance for the whole community being calibration parameters of the model. As this model has 7 factors for decision making, we need 2 parameters for sampling each ways, mean and standard deviation, resulting in 14 parameters in our model. Based on these factors, human subsystem simulates adopting new irrigation systems and changing crop pattern. These simulated variables goes to water subsystem. Using Penman-Montes, we simulate agricultural water demand, which affect farmers' decisions in the next year. After screening the uninfluential model parameters by global sensitivity analysis, we calibrated the remaining parameters based on 2 objective functions of national cliff of water demand and also area of flood irrigation systems, and we also validate are modeled based on national cliff of area of forage. This figure shows the result of one optimum solution given calibration and validation results. The performance of the model for this solution is acceptable given the national cliff for different outputs. After developing this mathematical model, now the question is what insights can be provided by such models for policymakers? To answer this question, we want to first assess time-varying socioeconomic factors that influence the agricultural rebound phenomenon, and second, to explore ways to avoid the agricultural rebound phenomenon to support sustainable water management. For the first objective, we perform a time-varying global sensitivity analysis on the developed model, which can adequately represent the dynamics of agricultural water demand in response to farmers' adaptation to drought in the Bow River Basin. This time-varying global sensitivity analysis on our developed model provides valuable information about the dynamical nature of the model behavior and comprehensive insights into the co-evolutionary dynamics of the underlying system. For the second objective, we use the result of the time-varying global sensitivity analysis and the gain insights to explore strategies to control the agricultural rebound phenomenon with the support of the literature. So this is the AGU model that we develop, and these are the factors or a group of factors in the model. We want to explore the effect of individual factors and also their interaction. The result of sensitivity analysis shows that the economic group is the most important element and has high parameter interaction. The irrigation expansion factor has increasing long-term individual effect with almost no parameter interaction, and the social interaction factors has decreasing effects with time and has high parameter interaction. The sensitivity analysis results show that irrigation expansion increases the rebound phenomenon in the long term. Economic prosperity was a key goal of Alberta's Waterfall Life program. However, from a sustainable development perspective, improving irrigation efficiency along with irrigation expansion in the Bow River Basin is likely to result in the rebound phenomena. Thus, to prevent the rebound phenomena, improvements in irrigation systems could be accompanied by restrictions to irrigated areas. Another strategy to avoid the rebound phenomenon could be to reassign water allocation to reduce farmers' water insights. As the AGU model includes crop yields in the economic functions of individual farmers, any reassigned water allocations would affect the dynamics of water use and then the rebound phenomena. Recent studies also showed that farmers with high water use could be motivated to reduce their water use when they compared their own water use with the average water use of their neighbors. Our analysis of the AGU model also identifies social interaction as the second most important factor. Therefore, raising farmers' awareness through formal channels may lead to a change in the dynamics of the rebound phenomenon. In conclusion, the AGU model demonstrates how farmers' attitude towards profits, risk aversion, environmental protection, social interaction, and irrigation expansion explains the dynamics of the water demand and the rebound phenomena. Economic factors dominantly control possible rebounds, although social interaction among farmers is found to be less influential than the irrigation expansion factor. Its interaction effect with other factors become more important, indicating the highly interactive nature of the underlying socio-hydrological system. Based on the insights gained via the model analysis, we discussed several strategies including community participation and water restriction that can be adopted to avoid the rebound phenomena in irrigation system. This presentation is based on 2 published papers. Thank you for your time.